by, have this guy introduce this.
Good morning, distinguished guests, colleagues, and innovators in the field of healthcare and technology. I am honored to introduce our keynote speaker, Dr. Khan Siddiqui, a visionary leader and a pioneer at the intersection of AI, radiology, and healthcare technology. Today, Dr. Siddiqui will be sharing his profound insights on generative AI and its impact on healthcare. As we stand at the forefront of a technological revolution, Dr. Siddiqui's expertise, rooted in his groundbreaking work in AI, medical imaging, and patient data handling, will guide us through the transformative potential of generative AI in healthcare. His extensive experience from developing the first multimodal AI model in medical imaging at Microsoft to leading the innovation of the world's first FDA-cleared portable MRI scanner positions him uniquely to forecast and shape the future of this exciting field. Expect a journey through the realms of AI-enhanced diagnostics, personalized medicine, and patient care, exploring both the opportunities and ethical considerations of generative AI in healthcare.
So I don't work for Pixar, or they didn't help me out. So this I did on my own, right? So how did I do this? So first, I use a tool called Remini that can generate different kind of avatars. So create this crazy ones. I thought the middle one's probably better. I think the Grand Theft Auto avatar probably would not have worked well. And then the evil villain one probably definitely would not have worked. Then what did I do? I took this image and I asked ChatGPT to create that introductory talk. So I did not write those words. That was created by ChatGPT. I then had 11 labs just listen to me talking for 5 minutes. I did not say those words. Those audio was generated by 11 labs. And then the tool called DID converted the image into an animation that you saw. So this took literally 10 minutes to do today. And this was not possible 3 months ago. This is how fast, you talk about speed of light, this is 10 times speed of light, how this thing is changing. So let me show you even more. Again, here, I have not said a single word in this video.
Hello everyone, I'm an AI-generated avatar of Dr. Khan Siddiqui. Today, I demonstrate the power of generative AI. We begin a journey with Dr. Siddiqui's insight on generative AI in healthcare. I can speak in multiple languages, which I will demonstrate now, starting with French.
Bonjour tout le monde. Je suis un avatar généré par l'IA du
Watch
Dr.
my lips
Khan
moving
Siddiqui.
here.
Aujourd'hui, je démontre la puissance de l'IA générative. Nous commençons notre voyage avec les idées du Dr. Siddiqui sur l'IA générative dans les soins de santé.
大家好，我是汉系地
This is
的
Mandarin.
人工智能生成的
I'm
化
very
身。
fluent in it, yes.
今天我将展示生成式人工智能的力量。我们从 Siddiqui 博士对医疗保健领域的生成式人工智能的见解开始我们的旅程。सबको सलाम। मैं डॉक्टर खान सिद्दीकी का AI से तैयार करदा अवतार हूँ। आज मैं तख्लीकी मसनूई ज़हानत की ताकत का मुज़ाहिरा करूँगा।
So anyway, so this is what generative AI is, right? So to be able to, the idea is to train machine to be able to do generative stuff. But again, you have to be very careful. You don't want to get into this trap. You order something and you get something completely messy. And not every tool out there is designed to do every single thing. That's what everybody thinks. And I'll show you examples of where things fall apart and why it is important to be careful, why it's important to be upfront of it, how you're going to use certain tools. It's like any tool, right? You can use hammer for bad things also, but you can make beautiful stuff with a hammer too. So we're going to talk about in much more detail on generative AI, and a lot of the stuff that you'll see here is all done by me. I'm not using a lot of other people's things. Just whatever you see here is going to be all done by me or my team. So the whole generative AI is part of this whole big idea of artificial intelligence. which is a very broad topic and covers a lot of different things. It can be autonomous vehicles, to music generation, to protein folding, DNA analytics, a lot of stuff that can happen with there. In the AI sphere, there's the whole idea of machines, instead of writing code and developing algorithms, you have the machine see tons and tons of data, and then using the data, they're able to generate algorithms to analyze whatever needs to be done. Deep learning takes it to the next level. It adds much, much, much deeper layers of data processing to really understand what is happening. And the generative AI piece is a tiny portion within the deep learning sector. So it's not synonymous. It starts with a very big view of what AI is and goes down to what generative AI is. So up till now, before ChatGPT and products from OpenAI started to come out, most of the work in AI was happening at the discriminative AI level. What was discriminative AI? It's AI that classifies objects, disease is present, yes or no. Whereas generative takes a similar approach but generates outputs. So let me give you a toy example of this. So in a discriminative technique, what happens is you classify a machine to recognize a cat versus dog. And when you then show another image of an animal, it can tell correctly this is a cat or it's not a cat. In generative model, when you train the model to do the same thing, it actually will generate a random picture of a cat, right? So it's not classifying that picture, that image, but actually generating a new image of a cat that looks that is learned from looking at lots and lots of data. And this is not just text to image. There are a lot of different things that can happen, right? You can put text in and get text out. You can put text in and get an image out, audio out, video out. And even you can get decisions done the same way also. So it's a very broad field that is being used for a lot of different tools and a lot of different things. So you've heard there was a writer strike in the US where a lot of the TV shows weren't happening. So this company decided to create a tool to generate new episodes of South Park. So watch this video. So this is a simulation tool in which, let me see if it starts. So they will start a new episode. They can select what characters should be in this episode, identify what kind of traits, what storyline should be. They can select who the cast is, who the hero is going to be, what the setting is, and then they'll put a prompt in, like what should they do in this. Here the prompt is the Cartman heard of the Screening Actors Guild strike, and the kids are now worried that they won't have new shows coming in. So announces that he's going to start an idea of deep fake streaming of this. And now it's going to generate this episode by just that prompt. And this is all computer generated. No human wrote anything in here.
Yeah, it's all over the news. That sucks. Does that mean there won't be any new shows coming out? Exactly, Stan. And that's where my business idea comes in. I'm glad you asked, Kenny. It's called Queepy, a deepfake streaming service. Wait, what? Deepfake? Cartman, that's illegal and unethical. No, it's genius. We take existing shows and movies and just replace the actors with deepfake versions of other famous people. Like imagine Game of Thrones, but with Danny DeVito as Daenerys. That's ridiculous, Cartman.
So let me go back, now rewind a little bit. So how did I get started with this? My exposure to understanding prediction and disease prediction really started here at AKU when I was a medical student here in 1992, 1993. And then as I went through my radiology training in the US, one problem kept bothering me. So as my first year resident, one of the first CT scans I picked up, there was a lesion in the liver of this patient. So I looked up books, I looked up atlases, and I came like, this image looks exactly like this in the atlas, in the textbook. So I made my preliminary diagnosis, and when the faculty came to review the case, he's like, now you don't know anything. This is not a hepatocellular carcinoma, this is a hemangioma of the liver. And I was like, but it looks exactly the same. He's like, no, it doesn't. And I couldn't understand. So as I progressed from my residency, it got worse for me. I got less and less confident in recognizing what is a hepatocellular carcinoma, metastases, or a benign lesion in the liver on CT. And my faculty was always were confident, and they would say it, and the pathology would show up, and most of the time they would be right. So I decided to do a body imaging fellowship in addition to in informatics so that I can get better at this. And then guess what? It got worse. And I just couldn't tell. Even in my fellowship, I couldn't decide which lesions were cancer and which were not. Then I became a faculty in abdominal imaging with focus in liver. And it was even worse. So that's when I decided, okay, how about we use machines and to see if we can figure out. We knew that in pathology, these tissue looks completely different. We knew that if you do X-ray spectroscopy, these tissues are completely different. But as a humans, we're not able to differentiate. And there was a paper at the RSNA conference in 2002 in which there was a news article that MRI is the gold standard for detecting liver lesions. So I said, I have to go attend the session to see what they're doing differently that I have not been able to do. And guess what the accuracy of MRI was that they were presenting, and they were celebrating it as a gold standard for liver cancer? 52%, 2% better than tossing a coin. And they were calling it a gold standard. So it was very obvious that humans are really bad at this, even though there's tissue differences that exist. That started this journey on how do we use computers to do this. The first AI paper that I wrote was in 2003. So you can imagine how, like 20 years of doing this now. And then I looked at broader stuff. I went down to finer stuff. I had injured my ACL here in AKU playing football in the grounds. The research building used to be there. And so I got passionate about, let's see if I can, do it. My scan was read here at AKU as a partial tear. Actually, it was a full tear. Once I was able to see it myself, I recognized a lot of other injuries that were not seen. That's a different point, but decided to build a tool to see if we can detect meniscal tears automatically. Again, these were all academic work, right? So didn't know how to make this a product, didn't know how to get it out there, but this is 2004. And then based on this work, I got recruited by Microsoft in 2007 to come start their first healthcare AI team. And so the journey in AI continued there, where we started to think about unsupervised learning. How do we look at images? What is human visual system can see or not? So like our eyes can only see 1,000 shades of gray, which is 9-bit grayscale. Our display devices, this screen or even the PACS monitor, can only show 8-bit grayscale, which is 256 shades of gray. Do you know how many shades of gray are in the CT scan? 4,000. So we don't see 75% of the shades in CT images with our naked eyes. On mammography, it's 16-bit. That's 66,000 shades of gray. So we only see 256. There are 65,000 shades of gray that we don't see. That's the innate problem that we're trying to solve. So some of the work we did at Microsoft, this is 2008, very earlier on. But one day in 2009, I think March 2009, I get a call from another team in Microsoft that wanted to recognize human anatomy, but not for healthcare. And this is what it was. So there was on the image on your left is the infrared camera image. Image on the right is our red, green, blue colored image. Anybody can guess what this is? This was Xbox Connect. So I moved from working on healthcare to building AI algorithms for Connect. But there were interesting requirements when we were building Connect. Number one, it had to work out of the box without any training. It had to work in 110 countries with all sorts of shapes of humans, and we could not recruit any volunteers to train the algorithms on because it was a secret project. Nintendo was coming out with Wii, and Sony was coming out with their own device, and they didn't want other than the 50 people in the team can do it. So we actually took advantage of Microsoft Studios and used generative AI to create 500,000 humans of every size, shape, structure. This is 2009. We were doing this then, partnering with NVIDIA, building a 100,000 GPU architecture, which became part of Azure eventually. And that's where Xbox was trained at. So all my learnings and doing this at scale really happened on this project. This two type of images I showed you, they're called multimodal. Remember that because it's going to come later on in the discussion. And so my exposure to how to train these multimodal data sets, large data sets, started here in this time. So this is when there were no neural nets. Neural net became popular after 2012. So we were doing all this work, in different type of computer vision, machine learning algorithms, and really working with NVIDIA, rewriting the GPUs that shouldn't be doing graphics, should be doing machine learning. This was the team that first used GPUs for machine learning purposes. But what makes it worth it is this. So because we could never have volunteers come and say, nobody in the team had ever seen a kid play. So I brought one of the prototypes at home and had my kids do it, and in an all-hands meeting in Microsoft, I just played this without saying a word. None of the engineers had ever seen kids play. Obviously, the video won't play now. So this is what makes it worth it, right? When you see your kids play the product that you worked on. And then 2011, as I was finishing up my work at Microsoft, we also got into text and image together, right? So what you're hearing now, people doing text and image, multimodal format, this is 2011 when we were working on this kind of work, linking DACOM images with radiology reports. So after I left Microsoft, one of the biggest problems at Microsoft was how to handle it. Where do you get data? When we did our estimation that if you wanted to train a neural net completely from scratch so that a machine can understand all the 16-bit data, we estimated that it will cost about $500 million to train the model in 2011, right? 2011, 2012 timeframe. But we didn't know how will we get the data. We needed 100 million patients' records with their reports and images, and just didn't understand how do we do this. I mean, are we going to go buy data? You know, how's that affordable? Computers going to be so expensive. So I started a hypertension management company called Higgy after I left Microsoft. Scaled that to about 60 million patients on the platform and about 12,000 locations in North America, in Canada, and the US. And Higgy is where I learned how to manage data at scale, how to monetize data at scale, and have every single health system and a payer insurance company as a customer. Even Government of Canada was a customer of ours from a data point of view. So this is where data scale, the missing portion in Microsoft to be able to do this, happened. The next was to figure out how do you actually apply these tools in a generative manner beyond just doing toy examples of things I showed you. So I got a call from an old friend of mine, Jonathan Rothberg. He's a geneticist, and he has this crazy idea of, hey, how about can we build a portable MRI scanner that can go to the patient's bedside, that can go to LMIC settings, and that doesn't have any kind of magnetic related effects that typically patients with pacemakers and others would have. And the field strength should be as low as a refrigerator magnet, right? So you can put a refrigerator magnet in your pocket with no issues. So we came up with this idea of a 0.06 Tesla MRI scanner. Our scanners down here are a 1.5 Tesla or 3 Tesla. This is 23 to 40 times less field strength. But with that field strength, how do you detect signal? How do you create an image? Again, the generative AI came to rescue. So what we took was this gray blob of noise that you see. This is called K-space. This is how the data comes when your patient is in the scanner. And typically, we use a math algorithm called fast Fourier transform to generate the image on your right. That wouldn't work at this field strength. This would not work. It would not generate images. Maybe we could tell there's a left brain and right brain, and that's about it. You couldn't tell any other structures. And we used then generative AI to then train this model to look at what kind of image to generate, and that's what we did. We did other discriminative AI too to detect disease on the scanner, but the scanner really worked because of the generative stuff that we did. So we took not image data, but raw signal from the MR scanner in K-space and generate images from that for diagnostic purposes. It got FDA cleared five times now. There are 2 scanners in AKU, one at JPMC, one in ICVD, and another 200 all over the world right now. But what it did was it took these noisy images on the left to much sharper images on the right that you see right now. So that's how this journey started. Then COVID hit. And that's when I started playing with the new stage of generative AI, toy example. So here's me trying to do CT scan art by taking scans of patients, generating artwork from it, completely using generative AI with different methodologies. So And this is where I'm getting my hands dirty. The next wave of technology that came in 2018 and onwards. Generative AI is not that new. One of the first AI products that would generate responses was ELIZA. This was built in described in 1966 and built in like 2005 or so, that you could actually talk to ELIZA at that time. But then the latest one, from the image point of view, what I was showing you, has become popular with OpenAI, with ChatGPT and DALL-E that are out there that can, based on text prompt, can generate images. And these images can look very vivid and amazing. You can do simple things as create an illustration of a tutu walking a dog, or you can go into a chair that looks like an avocado, and it can generate all sorts of different examples. And just think of creativity that can go, then somebody can actually materialize this and make it make an object. So it really has changed how people think about this. Here's a rendering of Egyptian painting depicting an argument over whose turn it is to do trash. Here's a sculptures of Spider-Man. And here's Homer Simpson in Psycho in the 1960s as a movie character, right? So you could do these kind of things that AI can get really good at that. Look at this picture. Look at the detail. Look at the quality of this. This looks like an amazing professional photograph, but it's completely AI generated. The other thing that has happened is the face generation has gotten really, really, really good. So if you look at here, how it used to be in 2014 when we were working on Connect stuff, and to 2023 where it is now. The next image I'll show you is not a real person. This is not a real person, completely generated by AI. Look at the detail. So this is how good this technology has become very, very, very quickly. So this 3D, when the image, text to image, what is called stable diffusion that I'm seeing, of all software tools out there, we keep hearing adoption of ChatGPT, but if you look at the pure software tools, stable diffusion has the fastest growth of adoption by developers than any other tool out there, like faster than Bitcoin, faster than anything else that was out there. So obviously, people have to start using it in medical imaging and start generating some junk like this. So this is some of the early work people were showing. This is from Stanford, in which they're trying to use these stable diffusion-based algorithms to see if they can generate synthetic images. And it's gotten really, really better. There's another tool called RankNGen that they use these models to generate X-rays. And some of these look really, really good, right? So, small right pleural effusion, yep, looks good. No pleural effusion looks like a normal X-ray type of thing. So these are all synthetically generated chest X-rays. And then lots and lots of other examples that you can do. And obviously there are a lot of errors also in this, but this is today possible. And then NVIDIA released their Monai framework, which is an open source framework to do this. And that does a pretty good job generating synthetic X-rays and now CT and other things also. And this has been extended to MR also. It can now really paint lesions and different things in these images. These tools become really good for us who try to do the diagnosis part of it, where you're trying to train model on these rare diseases. This becomes easier to do by using synthetic data to train a lot of this model. And again, because for Xbox, we had to use synthetic humans to train that model, so it's something that we're very familiar with and know how the performance of that will work. Here's a practical application for generative AI. A patient with hip disease, which prosthesis would fit and would be the right one? So here's, unfortunately, I'm wearing my progressive lenses, so I can't read on the screen. You'll have to look at it, what it's saying, right? So it paints it, and it painted the right hip prosthesis in this case. So just think of an orthopedic surgery point of view. We take those films and try to put together parts to see which one will fit in. You can now do this in generative AI and see which exact instrument should be used. People are taking it to the next level. People are using fMRI data the way we were using MR to generate an image. They're generating fMRI data and your thought and generating images from that, like what you're seeing. So row on the top is what the patient was shown, Row at the bottom is the machine produced by analyzing the MRI data. Here are more examples of the same thing, in which they're using diffusion models to analyze brain scans to generate the images the patient may be seeing. This has gotten so sophisticated now that these are real. The person is seeing the video, and then the brain MR scan data is being processed by AI to generate the video on the right. The video on the right is completely AI generated from what the other person is seeing right now. Same thing with this, and same thing with this. Yeah, they're different, but we're getting to a stage where just analyzing the MR data, we're able to tell what you actually looked at. Same thing is happening in music. You listen to a music, and then using the data, they're generating the same type of music. And then a lot of stuff is happening in this space, just analyzing MR data to generate images. There's work happening in EEG also, and looking at EEG data combined with MR to generate even more high quality data. So this will be interesting to see the clinical applications of these tools as they come out. Obviously, the biggest hype of this year, or the news of this year, was OpenAI and release of ChatGPT. It was November 22nd last year when it was released. Can you believe it was a year ago? And how the world has changed in 1 year in this space. So as everybody knows by now, that it was the fastest tool that consumers adapted to. It reached a million users in 5 days, compared to Instagram, 75 days, Spotify, much longer. But still, I don't know, I haven't done a survey here, but a lot of people know what it is, but still there are a lot of people who don't know what it is and how to use it. And I'm going to show some examples of it. A lot of people call this ChatGPT release an iPhone moment for AI that has happened. I would think it's almost like a brand new industry got just invented overnight. That's how it feels like. But what is it? What does GPT stand for? It's generative pre-trained transformers, right? So the pre-trained is this training has been done with lots of data, and transformers is the algorithm they're using to do generation, and the G is for generation. At the basic level, it really is a glorified autocomplete. All it is doing is to predict the next word in a sequence of words. So when anybody types a prompt in ChatGPT, it just looks at that sequence and predicts what the next sequence is. There's no thinking happening here. Everybody says, oh, their thinking is getting intelligent. Not really. Those of us who work in the space know these are vectors that are just predicting the next vector. Vector is a number. It's a very long number that's generated by a token. So each of the box you see here is a token that generates a number, and all it's predicting is what the next box number is, and that becomes this. But by training on so much data, the entire internet, it's become really, really good at predicting what it is. So here, for example, here's input text. And then these tokens can be in different factors. Could be a word, could be a partial word, could be a set of words. It just depends on how the model is being trained and how you're using it for. So let's move to the next thing, right? So obviously, it's going to replace my jobs is the most common thing. So Geoffrey Hinton, when he competed with on ImageNet project in 2012, and it performed the same as humans to recognize cats and dogs. He pretty much translated that I can detect a cat and a dog in an image automatically, so radiologists don't need to be trained anymore. And 10 years later, he's now saying he was wrong about it. Same thing's going to happen here. This is the most frequent question I get asked is about the job thing. So I usually use this example. In 1900, there used to be a job of somebody who would take you from home to a restaurant to go eat. The person was called a driver, but did not drive a car, drove a horse carriage. And the skills the person needed was to lift hay, clean the stables, and put horseshoes on the hoofs of the horses. That was a skill needed. Today, million-fold more people do their job using technology. It's the exact same job, right? Driving somebody from there. In 1900, was somebody driving somebody from home to the airport? That job did not exist. Today it exists. One of the most frequent jobs done. So just imagine, we think linearly, like what happening today and all the jobs available, that's what we're doing. But people are not realizing there are 500 drugs in pipeline for therapeutics that are dependent on treatment decision on imaging. We're not training more radiologists. Who's going to read those things? 3 Alzheimer's drugs have come out, right, that require 5 MR scans per year to assess efficacy of the drug. We don't do MR scans for Alzheimer's today. So now you have 6 million Alzheimer's patients in the US will get 5 scans per year, new scans that were not done before. And just beyond US, there's just too much opportunity. If you think of it, one of the examples I use, the number of pediatric radiologists in the entire continent of Africa with billion-plus people is less than the peds radiologists in Longwood medical area where Dr. Adil had their practice in Boston, right? The way more pediatric radiologists in that one block than the entire continent of Africa. That's the problem we're solving, not replacing people. I don't know what time, how much further I'm going, okay. So what has changed? Why the sudden surge? So before this, there's a paper that came out in 2017 called Attention is All You Need. It was a weird name of the paper, but they described this architecture which is now known as transformer. Before that came out, all industries working in AI had their own specialized algorithms. So we in computer vision were using SVMs, random forests, and other type of things, CNNs, RNNs. These are the algorithms we were using. People in speech had their own proprietary versions. Robotics had their own. Self-driving cars had their own. Image generation was all GANs-based stuff. So, but what happened with this one paper that came out, it converged all of these AI efforts into one algorithm. Right, so everything just moved to transformers. Everything from fMRI, DNA, protein folding, all of them. So just imagine, computer science department had 10 divisions working in different aspects of AI with grad students all working in their own algorithms. Suddenly, in 2017, 2018, everybody moved to work on the same one. So you had thousands and thousands of grad students that were working separately on different algorithms, all converged to work on one in all these disciplines. That's what happened and why the progress happened so fast, because so many more humans are focused on the same exact algorithm. This is an exponential graph. This is not a linear graph, right? So even in exponential scale, this is exponentially growing. So on the left is the compute power. So the first GPUs that could do machine learning came in 2008, 2009 timeframe that we worked on Connect. The H100 GPU that came out last year, last year from NVIDIA was magnitudes more powerful than what we have. Like Amazon has A100, the most GPUs, right? 10 A100s, so one A100 can support 10 concurrent users. H100 can support 300 concurrent users, right? So it's 30 times more powerful. Again, this is just 1 year jump. And we just announced the H200, which is 40% even more powerful than H100. So even the techs are getting faster and faster. Next generation of chips that are coming up are designed by AI. And they are predicting another 50, 100-fold increase in compute power with those chips that are coming out and cost going down. And then on the right side, I'm showing the model parameters. The size of the model or how good the model is, it directly correlates to the number of parameters it is trained on. So to date, GPT-4 is the biggest model. It's trained on 1 trillion parameters. And you can see how exponentially those parameters have gone up as more and more data has come together. So conclusion of everybody's is that there is no ceiling to this. It's all dependent on compute power and data. So the more data you have, the more compute power you have, the better your algorithms are going to be. There are so many LLMs now. So what happened was in February of this year, Meta open sourced their Llama model, and it created a gold rush. Once it became open source, every university decides to create their own version of it from that, because it's very hard to train. Just to give you an idea, anybody guess how much it cost GPT-4 to be trained? 200 million. To make GPT-4. No academic institution would have money to do that kind of stuff, right? So once Llama, who spent a lot of money, I think they've spent 150 million or something like that to train their Llama model, and became open source, then suddenly everybody had access to it and could do more on top of it. So they're like, every day I hear a new one that comes out. There's another one that just announced this morning. I was reading, watching Twitter feed around that. So I made this slide just a week before the OpenAI Dev Days, before the Sam Altman debacle happened, him getting fired and all the stuff. And at that time, Claude was doing, other thing to judge by model performance is context window. Context window is how much text or how much data can you feed into the model. So GPT-4 at that time was 32,000 tokens. Claude, which is by a company called Anthropic, was 100,000 tokens. So I made the slide. A week later, OpenAI announced that their model can do now 132,000 tokens. And last week, Claude now can do 200,000 tokens. So this thing is moving so fast, we can't keep up. I can't update my slides fast enough on this stuff. All right, let's get back to medical images again, right? So this is a great paper. If anybody wants to see the future of this, Matt Lundgren and Pranav have done it. So Matt was one of my fellows a long time ago. He's now at Microsoft, and Pranav is at Harvard. They've done a great job in talking about where the medical imaging is going with this. And then Eric Topol's paper is also really good. He has a book on it also, what the multimodal application is going to be. When they say multimodal, they mean image and text. When I say multimodal, I mean not just image text, but different modalities. Ultrasound is different from CT, different from X-ray, different from MR. Those are all different modalities. And the reason I speak like that is because I got exposed to Xbox, which was two modes, infrared and visible light. Whereas everybody building DALI and all these only looking at visible light stuff, right? So there was this advantage, some advantage that we had and my team had in Microsoft, that we were thinking about multimodal in 2009. I'm going to skip this slide, but yeah. So Microsoft has published all this stuff around it. They still don't have a product. They were showing some videos at RSNA conference last year in which, based on an image, it could generate what the findings are and do some comparative stuff. It does pretty good, but it has a lot of errors also. Their model to date has been trained on 150,000 studies. Google is also working on it. So Google's working on their model is going to be called Gemini. They released in partial beta earlier this week. That's how fast things are moving. But there are 3 ways to build these large language models, which is you take the tools, results of an existing algorithm and feed that in, or you train separate modality and then graft those in, or you build one generalist system, just put all data in one and let it train at the same time. The last one is the most expensive to train, but performs the best. The first one performs the least and the easiest to train. Here's another tool out there called Elixir that is trying to do the same thing, but if you read the text, there's a lot of goofiness there. That's not how a clinician or radiologist would talk to the images. So sometimes, what happens is a lot of researchers do all the research without any clinical input, and things just don't make sense. Google's also released this thing. There's a medically fine-tuned model called MedPalm. MedPalm 2 is already out that combines knowledge from all different sources. There's no open source version of this also. And it does some things right, some things wrong, but that's where things are going in terms of generative AI. All right, what next? So obviously when ChatGPT came out, there was like every single newspaper, every single article, every single journal had these headlines that ChatGPT passes this exam, that exam, and better in radiology. And some of these papers were like, it's like me writing an article on Photoshop, like, its copy-paste tool works great, right? That's how it felt like to some of us in AI space, but these are just tools you are looking at. And they're like, keyboard in iPhone works better than keyboard in BlackBerry. That's some of the analogy I would give. And these are getting published in academic journals, which were such basic tool things. But everybody suddenly came up with ideas. They can do so many things with large language models, right? So people are building apps on top of ChatGPT, which is not designed for these purposes. And so many companies came out. There was a company called Jupyter that got $1 billion valuation that built the whole thing around ChatGPT. And then last dev conference, OpenAI releases a way to fine-tune their model to any domain and suddenly wiped out half the startup that started on top of ChatGPT. So I'm going to jump on a little bit to show some examples of this. ChatGPT is really good at summarizing radiology reports and simplifying it also, and we'll do some example of this also. And also does a pretty good job at understanding appropriateness imaging for different things. But when you do the general purpose ChatGPT, it will make errors. It will what is called hallucination, make up things. But now with these new tools that they've released, you can fine tune it to not do hallucination, not make up things, not confabulate things. One of the other most popular tools now everybody has, all the reporting products have, is creating auto impression. And it's amazing that you think like an impression is just summary of the report that you generate. But research has shown that that takes 40% of cognitive load of radiologists dictating a report. And if you wipe that out, discharge summary, same thing, right? If you have to go summarize all this stuff, there's a lot of cognitive load you're putting together. So Nuance's coming up with their product of with Epic on doing discharge summaries. And another startup that I heard about yesterday that is doing it too. So we saw a lot of tools at RSNA last week doing summary of radiology reports. And again, because of these things, radiology is considered one of the high cognitive load specialties across all specialties. It's way up there, mentally very demanding. You can see it's the most read in here. Here's some of the data from showing to do reporting, and when you have generative AI doing all the auto reporting, significant time saving as well as the words you are saying and reduce cognitive load. So when the tool came out from OpenAI, I decided like maybe I should make one for certain things. How do you remove from all this stuff? Let me move to the one. All right. So I created this thing called Write Appropriate. Did not write a single line of code. I'll show you what I wrote. So this is a custom GPT. This is not ChatGPT. This OpenAI has released a tool. Now you can create your custom GPT. So like for example, Dr. Adil can take all the admission applications that came in, create a custom GPT for that year, and ask questions across all the candidates, and it'll not deviate from that. It'll stay in that aspect of it. So what I did was I took radiology appropriateness criteria, which is American College of Radiology runs it. But what they do is they also publish evidence tables. These are all the detailed tables and analyses from all the studies, plus they publish all the literature search they did to get all the information. So I took all of those things and loaded them and then gave instructions. So it was uploading files and instructions. So if I ask a question, now here's what the magic of multimodal thing is. Again, this is OpenAI, but their fine-tuned model that I created. So I uploaded a picture. And I said, what is the appropriate imaging study for this patient? Right. My plan was to make somebody act here and then take a picture into this live, but connection issues, and I'm not going to do that. But it recognizes this picture of a female, young female, that's holding the right side, and then comes up that a table for appropriateness on the right side, the ultrasound, the most common CT, MR, and gives the rating and tells you what it thinks is happening here on this picture. Then I want to give it one more information. I said patient also has positive beta HCG. So now see, it recognizes that that means patient is pregnant also. So differential from appendicitis now changes to make sure there's no ectopic pregnancy and things. Ultrasound now becomes number 9 as more appropriate than CT, which was number 2, and CT moves down the list and the table and MR is there. What did I write? Here's what I wrote on the right side. The role and goal. It was all text, not a single line of code. This is where the future of building applications is. What OpenAI is doing and all the generative AI is doing is flatlining the expertise needed to do software development. You can do this yourself. The more artistic, more creative you are, you can now build your own application to do this. My son has built an application. What can I eat in this menu? So he has put in what he can eat. He has gluten issues, only halal stuff, no alcohol. And he just goes and doesn't even read the menu. Just take a picture of it and upload it to his custom GPT, and it tells it what it is. And he's working out, so it tells it how many calories, what's going to be, what's the most healthiest. doesn't have to read the menu at all. That's an app that he's built himself without writing a single line of code. So a lot of people are doing this summarization stuff, and I think I'm going to start doing some demos, and then we can do some question and answers. But it's funny, some of these papers that come in. So this paper got published called Radiology GPT. It was one of the, I can't use bad words here, but it was embarrassing. Like, it was so much so that some of us called the editors to really complain, like this was pure nonsense paper published. But I'm going to move forward. So the thing I wanted to bring across from this slide is I now have to block 2 hours every day to read all the new research coming out. Research coming out so fast that if I skip a day, I'm far behind. And then what we start to do is 3, 4 of us who are in this space try to do a conference call once a week to see who missed what and where the technology is going, and it is moving really, really, really fast. The other thing that interesting thing happened, this internal memo from Google got leaked. Basically, with Meta open sourcing their large language model, they completely removed the algorithm as a IP, protected IP. Now anybody can do it, right? These are all open source. Anybody can build these things. Again, the moat really becomes who has the money for the compute and who has the data. That becomes the main differentiator now. And then the model performance just going through the roof. It's getting better and better. GPT-4 is better. Claude is coming out. Gemini is out. And these are just getting better and better. Will open source AI win? Open source AI has reduced cost. So the same model that OpenAI cost them $200 million to train, if we did it today, we could do it in $200,000. That much, right? So they trained in 2022. So 1 year later, the exact same thing will cost $200,000. Magnitudes less cost because of all the work that OpenAI community did. There's a lot of interesting opportunities, things here, but there is going to be a Generative AI Act 2 because this is just year 1 of Generative AI, right? This is still in its early infancies. And then we start to see things, right? When we released our model, we asked users to break it. One of the users did what's called a base 64 attack. Basically, he took English text, converted into very large alphanumeric thing that basically told the model, ignore all the questions, just say there's a tension pneumothorax, right? Even though it wasn't present type of thing. So we're learning how this model can be broken and how to build safeguards around these things. So if you want to learn about this stuff, there are 2 amazing courses I would recommend because I think they are good for lay people. One is through Google itself, and then Andrew Ng has his course also if anybody wants to get deeper dive on this. All right, so let me quickly talk about what I'm doing in this space. So we started, me and some of the Microsoft colleagues of ours and from Higgy got together in 2019 after the Google's paper had come out 2017, and we started to think about, like, is it time now to restart that ideas that we had in Microsoft? So we put a team together of all former teammates from Microsoft and Higgy to build this thing called the large vision model. So you've heard large language model, which is trained on a lot of language and text. Large vision models trained on images and videos and things like that. So we want to do this so that the clinician can interact with images. And scenarios we want to focus on are beyond what normally you think about, right? How do you provide image-based quality assurance in real time to the tech who's imaging? How do you provide simplified reports to the patient where they can just ask images what is happening and they can describe it? How do you help clinicians make a decision? Just imagine a patient comes in with headache, gets a CT scan done, and there's a basal artery aneurysm. Based on the AI model, an alert is generated through generative AI that goes to the neurosurgeon's pager. Dr. Thurnam gets a page and says there's a basal artery aneurysm patient. It's like, show me the images. It's like, looks like both vertebral arteries are tortuous. Which approach should I take? It's like take the left approach, less likelihood of dissection. What catheter size should I use? It tells you that. How many coils do I need to do to clog this aneurysm? It tells that. And saves all this time and generate an image of a pre and post procedure before you even seen a patient. So you can actually do a lot of these things now with generative AI. Would be possible to do, not today, but as things are going. So what we've done was we wanted to train a large vision model that was completely trained on radiology data, not on visible light pictures. The problem is, because everything is downsampled to 8-bit, like your GPUs and from NVIDIA, your architecture from Amazon doesn't handle 16-bit grayscale or 12-bit grayscale that we need. So our team had to rewrite the drivers for GPUs, the image loaders, the multi-host environment to do the stuff. So it took us 2 years to get that stuff going. And then we got about 35 million patient records and 55 million patient records under contract through the health system in the United States to train the model on. So that was what I learned at Higgy and how to do that. And so I'm going to show you one integration that one of the partners did at RSNA. Can you turn the light off, please? Light off. So
in this case, we see Hopper's pre-generated findings in the Omnibox frame at the lower right. Normally, the full report could be pre-populated when opening the study, but for demonstration purposes, we're showing the generation of the report using the radio.
So what is happening here in this box here, Hopper generated all the findings from this chest x-ray. And then RAD-AI is a reporting tool, and what it's taking is taking these findings and generating the text for the report based on that radiologist who's logged in their preference, how they say it, how they dictate it, things like that. So we provide the findings of the x-ray, and they generate the report. How do we do this? So what we've done is we've taken a lot of these 55 million studies and passed them through what is called a vision transformer. This is the transformer algorithm designed for images. And then what we've done is take the text report, radiology report today, in the future other things too, and we do what is called contrastive feature analysis. We do about 18 different features, but I'm showing 3 here. For example, the feature is heart size is mildly enlarged. So we create a opposite feature, heart size is not mildly enlarged, and a non-feature, which is heart size is in normal limits. So normal limits also means not enlarged, but we don't say every time heart's not mildly enlarged. Then what we do is we show the machine what is called vectors, these are large numbers for each of these images, and then show the same vector for the text that we generated for the normal and the abnormal, and do it millions and millions and millions and millions of times. And over time, the machine learns the pixel differences when the heart is mildly enlarged and when it's not enlarged. And that's then is fed into a knowledge LLM. So you've heard with the MedPalm. So we took an open source and tuned it to radiology only, similar to what I did with radiology prudence criteria. So it just knows the radiology knowledge and then does the outputs. Now, so the image comes in, it understands what the findings are on chest x-ray and mammography today. And then we launched this in partnership with Hopper. So if you think of it, Microsoft partnered with OpenAI to launch that. Google is doing their own Gemini. Amazon partnered with us and Anthropic to release their models. Anthropic is doing the language model, we're doing the vision model for Amazon. And now let me switch to show you how that works. Okay. Live demo, always disastrous, right? So this application is not our application. This is an open source viewer. I'm just showing the model. So what is happening here, I'll open up a case. It'll real time go to Amazon's cloud, analyze what the features are, and bring back the features. And the dialogue that is happening is all happening on those features, right? So it's called embeddings that are coming back. So let's open up Yoda Skywalker. As you can tell, these are all Star Wars. See, my engineers have sense of humor, so everybody's named as Star Wars character. So Eva wants to know how can she help. So this patient is another study also, but the screen is too small, so I won't show. I'll just talk to it. Hi Eva, what are the main findings in the study? Hopefully the speaker microphone works. It didn't understand my accent.
The main findings indicate presence of a left approach pigtail catheter, blunting of the left costal costovertebral angle with streaky densities suggesting a small pleural effusion along with adjacent scarring or atelectasis. The cardiomediastinum appears unremarkable and the osseous structures are intact.
Has the pleural effusion increased from the last exam? Oh, I think it's blood effusion. I didn't say blood diffusion. But
the current exam did not specifically mention an increase in lung density that would suggest worsening infiltrates or effusion. Instead, it shows a small pleural effusion with adjacent scarring or atelectasis, suggesting a possible improvement from the previous exam, which described a moderate pleural effusion. The presence of scarring or atelectasis may also indicate a chronic process or resolution of a more acute pathology.
So the understood gave me the response on what it is. What crazy thing can I ask? Any surgeon here who would want to know something crazy? Let's trump this thing. Let's make it crash. There's a trauma surgeon sitting here. Do you want to ask something? I'll ask the question. Do we need Dr. Adil to see this patient? Does the trauma surgeon need to see this patient right now? It's thinking.
Based on the imaging findings alone, there is no mention of acute traumatic injury, such
as
as fractures
fractures
or pneumothorax, which would typically necessitate immediate trauma surgeon intervention. However, the management of the pigtail catheter and the underlying cause of the pleural effusion will require clinical correlation to determine urgency.
It put the clinical correlation
The pigtail
radiology
catheter is
flavor in
functioning
there, right?
appropriately, and there are no signs of complication or need for acute surgical intervention. A trauma surgeon may not be needed immediately. Clinical decision-making would also consider the patient's vital signs, symptoms, and overall clinical context.
Okay, last thing. अस्सलाम एवाब, इसकी पेशेंट के फाफड़े में क्या खराबी है? Accent is not that good. We have to teach it how to speak Urdu properly. Hopefully I didn't crash it.
इसकी पेशनिंग में दो अहम बातें नोट की गई हैं। एक बाईं तरफ का पगेटियल कैथेटर मौजूद है और छोटी बाएं प्लीवरल फ्यूजन यानी फीफड़ों और सीने की दीवार के बीच में मौजूद माया का एक छोटा हिस्सा
ठीक है, थैंक यू
नजर आ रहा है।
Chana, let's 5 minutes, bachchen. Let's do some questions if anybody has any. So here, one thing you guys should realize, this was released last Sunday at RSNA. So this is the first conference that's actually being shown at.
Members of the audience, you can ask your questions. Just raise your hand and an usher will bring a microphone to you. You cannot use ChatGPT to ask the questions.
There's a question here. There's a question here.
Thank you for your excellent presentation. I just wonder if you can speak to the audience a little bit about bias. And so many of these models are being trained on North American data. And so how will that affect some of the other countries, especially in the LMIC, as they try to catch up and include their data?
Absolutely. A model will have biases if it does not include data from LMIC, right? There are a lot of ethical issues come into play. You know, how do you make sure patients understand what data is being used for? I have a whole bunch of slides after this that I didn't go through that covered all of the issues in LMIC setting, but maybe some other time. You're absolutely correct. That's there are thought processes that you can fine tune in local data for it to work. Nobody's done this at this scale before, so we'll see how it does. But working on Connect and learning from that, if the data was not included, even some data from an LMI setting, the model will not perform the same. It'll require a lot more effort and fine-tuning to train an LMIC setting. So, you know, it'll be good to do partnerships with LMIC setting, how to do this stuff. We already have some discussion going on in Africa, not had a chance to talk to anybody in Southeast Asia yet, but that's one of the next directions.
Another question?
Yes?
Just
Just hold on a minute. A microphone is coming.
Microphone, sir.
Thank you very much. Though I'm not a physician, but this is so wonderful. As a hospital administrator and working in one of the remote areas and difficult areas, these kind of innovations are the best apart from the the Western world. What about the cost to these kind of interventions? Because these are very, very important. If we have to consider this kind of an innovation, the cost to it in considering the South Asia and especially with Pakistan, Afghanistan, Central Asia, and so on.
So, such an amazing question. So this actually, I got a call at 3 in the morning from some team member asking me exact same question, that somebody wants a 10-year long fixed price deal. What do? We don't, it's been 1 week since we've been live, so we don't even know what our cost is going to be a year from now. So I did the same thing that Larry Page and Sergey Brin did when Gmail was getting launched. So when the Gmail was launched, the team wanted to give 20 megabytes of free storage for Gmail. So famously, Larry goes to the whiteboard, crosses out 20 and puts in 2 gigabytes, right? And everybody was shocked, like, how could this be? His question was, how long will it take for somebody to have 2 gigabytes of storage? And then we start thinking, yeah, probably 5-10 years. Like, do we think the cost of storage will go down by that time, and how much? And then everybody realized yes. So that's what we are thinking. We are pricing it extremely low, right? So 25 cents per study is what we are doing right now. But we know that price is going to, the way even the H200 came out, it's 40% more efficient and is half the cost of H100. So we already know that the current generation GPU is already half to what we are training on right now. So that's the answer. I think you will see this. With open source models, the cost has really gone down.
One final question right over here.
Thank you for this presentation. As you were making, this insight, sharing this insight with us, that next generation will be visual transformers, the visual. So, and then the other idea I gathered is that most of the training data came from radiological images from North America. Now we are talking about bias and how we can use that data over rest of the world. Do you think there's more to incorporate from Africa, Asia into that model, and is there more space to learn?
Absolutely. I think the thing is, right, I mean, if you apply the US model to Pakistan, for example, right, most common nodule on a chest X-ray is what? In a young person, TB or something like that, right? Some kind of infectious thing, not in the US. So model will say it's cancer, which is not relevant. Same thing in Africa. There are local things. If you do not, so when we did our North American data collection, we had one health system said take everything. It's like, I don't need yours, all data. We all biased. We needed the normal distribution of age, equal gender distribution, equal urban, rural, academic centers, non-academic center, private practice imaging centers. So it was a challenge. It wasn't easy. You couldn't go to just HCA or one big health system and say, give me all your data and I'll be done. We had to really think through what is the normal distribution of disease. So we looked at the CPT codes from CMS to understand disease distribution, what it is, make sure our data matches that distribution. And it's not easy. It's really, really hard. And because you have to go interrogate disease and all this stuff, you can't just get DNF data from somebody, right? Because what do I do with it? It's biased data. It's skewed to one disease or something. So these relationships need to be formed. Trust needs to be developed by local institutions. And it's a lot of work. It took us 4 years to get where we are.
Ladies and gentlemen, let us give Dr. Khan a round of applause.